All right.
And Justice League,
Yeah.
it's like, what's your superpower? And he just says, I'm rich.
It literally is though for Batman. Okay. Anyway, let's talk thermo. So thermochemistry. Let me give you guys a rundown. Oh, that's not very good as a marker. Let me get you a different marker. You can write if you want. I'm giving you an overview first, and then what we'll do. Why are you flashing? Stop flashing. I'll give you an overview first, and then I'll give you the first bit of information for this topic. So, thermochemistry comes as a lead on from the structure and bonding. If you guys remember that one from last year, most of you guys would have said that. So that's what it ties to from level 2. So thermo would be chem 3.5. You guys, or sorry, 3.4 if you guys are looking it up, which builds from structure and bonding, which was chem 2.4 if you guys remember. So if you're looking things up, that's how you can find it. I looked up also the AS number as well, in case you guys want to Google anything for it. Once I find my folders. Here we go. The AS number, if you guys are looking for resources, is standards. Here we go. 91390. And I'll scan all this and I'll put this online as well. So don't worry if you've missed anything there. All right, so this one is one of the options for our externals. This one's worth 5 credits, just like organic is. If you think about the course for our level 3 chemistry with the internals, there's 3 internals. All of them are worth 3 credits, so you get 9 credits from your internals. If you pass them all, plus the 5 credits, you'll be exactly on 14 to pass your course for level 3 chemistry. If you want to sit 2 exams, because I'm mindful some of you guys are applying for health science and you need 18 credits, you sit both exams, you would then be at 19 credits. So you would meet that requirements for the health science as well if you take both of these exams. Comparing and contrasting thermo with organic chemistry, I personally find that organic chemistry, in my opinion, is easier to get merit and excellence on. There's a lot less writing for organic chemistry, but the downside is that you have to understand the whole topic to be able to sit the test, and you have to know how everything interrelates to each other. So that's what makes organic chemistry tricky for a lot of students, is that it's a lot of content to learn to be able to do it. Thermochemistry is a little bit easier in a sense that you can rope learn it, like structure and bonding. If you guys remember that last year, it has really nice categories of questions. The downside to thermochemistry is that it's going to require a huge range of skills. So you need to have that writing skill, because there's going to obviously be writing for some of those questions. You're going to need to have that math skill, because those calculations will be coming back in a slightly different format. So that's the challenge with thermochemistry, is that it requires a larger range of skills. I also would say it's probably harder to get excellence on, simply because the writing component is just as similar for other assessments with writing, that anything that you have to explain and discuss, you then run the risk of not explaining it well, and thus losing out some of your points. So those are kind of things to keep in mind for pros and cons. But I know some of you guys really dislike organic chemistry, so thermo is the way to go. Thermo goes into 3 categories of questions. It's very similar to structure and bonding, but still with notable differences. So the first question that you're going to get in thermochemistry, or the first category of question, is going to be, I'm just trying to think what order I should go in. I'll go in the order that I plan to teach it. So the first one is periodic table trends. So that's just basically looking at patterns in the periodic table and explaining why they are there. This question here basically replaces the types of solid questions. If you guys remember last year, you had the 4 different types of solids, the ionic, the metals, the covalent networks, and the covalent molecular, and that was one of your style questions. That is going to get replaced by this periodic table trends question. It's pretty straightforward. I don't know why that turned off. It's pretty straightforward as a question. It's not too bad. The thing to remember is that there are a little bit of chopping and changing between these questions. This is actually a Frankenstein standard, and structure and bonding is the same way. They were two old standards that they put together, and that's why it seems like a real mixed match of information, and it's because it was two separate standards. So there's going to be a lot of random stuff that's going to be asked in this exam. So with the periodic table trends, one of the things that's often nested under periodic table trends is going to be electron configuration. Which you guys might think, cool, that is so easy. We've done that last year. That was that, like, or not last year, throughout high school, the 2882 stuff. Except it's not. It's going to be a little bit more complicated. Did everyone sign the card? Cool, I'll take it. If no one else has missed out on signing the card. Oh, it's just for our guest speaker. For the guest speaker that we had for STEM. All right, so that's the first question that you're going to get. The second question you're going to get is your Lewis structure, shape, and polarity. Lewis structure, shape, and polarity, which is what you got last year anyway. So that's going to be similar to what you've previously done. The difference between this question and last year's question is that you're going to get some larger, more complicated molecules. Not too much of a big ask because it's, like I said, very similar to what you've done previously. Again, there's one of the little subtypes of questions that get shuffled in here quite frequently, and that is on melting and boiling point, is the way I like to describe it. With that melting and boiling point, it's really trying to highlight this idea of intermolecular forces. So if you guys remember last year how you did your types of solid question and you were explaining their properties based off of what's happening at the atomic level, both with the particles and with the forces that hold together that particle. So one of the things you learned about was the covalent moleculars, and the covalent moleculars have these intermolecular forces that hold the molecular solid together. So this year they're going to really zoom in and focus on that. And they were going to be talking about the different types of intermolecular forces and how that's going to influence those molecules. This question is often nested underneath the Lewis structure, shape, and polarity question because Lewis structure, shape, and polarity have to do with the structure of molecules anyway. So that tends to be put here. It's not always put there. Sometimes these two things get chopped and changed and moved around. Some years they're very nasty and mean and they do that, but generally these are the categories you're going to get. The last category is your enthalpy calculations. And that's what I'm saying. It has that range of skill sets. You need to have that writing skill. You need to have that math skill. With the enthalpy calculations, it's worthwhile revising the stuff that you did last year simply because everything from last year from 2.4 is fair game. So they might put in an older question from the previous year, or not previous year. I want to say older question. They might put a question from the year, what you would expect to be a year 12 question. I have seen them do that every so often just to kind of change it up. So it's worthwhile to revise that material from last year. But this year, the thing that the enthalpy calculations is going to focus on is something called Hess's law. So the calculation is going to be slightly different. The other thing that they'll be focusing on with the enthalpy is going to be entropy, which is the disorder and whether or not reactions will be spontaneous or non-spontaneous. So will it happen without any energy input, or do you need to put energy into it? So those are the three main categories, and like I said, it's really then easy to rope learn because there's those categories. Any questions so far? Good? All right, so for today's kind of tutorial for thermo, I wanted to start us on the teaching of it, and I'll start us with some real kind of basic stuff. We're just going to focus on the electron configuration for this first tutorial. I want to thermochemistry this electron configuration stuff is really frustrating. It's a lot for me to explain, and it's only worth an achieve point. So it's really frustrating in that sense. If you don't get it and you don't want to bother studying it, it's not going to hurt you dramatically because, like I said, it's only an achieve point. But I need to tell you it because we've been lying to you about how atoms actually exist. So that's why. And like I said, Blake was here on Wednesday, so he knows the lies that I've been telling you. All right, let me pull up the PowerPoint.
You're giving us the truth, miss.
Yeah.
What Grant's been telling us.
Yeah. Oh yeah, because I wasn't your teacher yet. So, what do I want to say? I don't know if they're necessarily lies. What we told you wasn't fully right. If that makes sense. So let me grab the PowerPoint. I did try to start organizing things. So that way I can kind of show you guys the key slides. And I'll put this up on Google Classroom. So we've already talked about that stuff. So if you guys remember in previous years, when you guys learned about atomic structure, we talked about how there was a nucleus with your protons and your neutrons, and then you had these electron shells, and that 2 went into the first one, 8 went into the second one, 8 went into the third one, and 2 went into the last one. And then everyone was like, what happens past calcium? Because this, if you look at the math, adds to 20, and the atomic number for calcium is 20. And then I think your teachers probably would have said, don't worry about it.
Yeah.
You just need to know the calcium, don't worry about it. And that's what I say to my students as well. Don't worry about it. If you want to know, you have to go and do level 3 chemistry. Otherwise, this model works fine if you're working at that level. So if you're not working at that level, which is what you guys are doing, is what you guys are used to seeing with atoms, and you think about atoms as being kind of like a solar system and the electrons fly around. That's not how it actually is, because it would crash into the nucleus if it was that way. So what actually happens is we have our nucleus, and we have what is called an electron cloud. Electron cloud you can still kind of think of as electron shells. Like the shell concept isn't gone, it's just adapting. So with this cloud, it takes a shape, and we're saying statistically, the electron needs to exist somewhere in this shape. So, and that's what you see in this model here, and oopsie, too far. That's what you see in this model here. Let me get my laser pointer. And you see how that little red dot is popping around? That's what's happening with that electron. So it's existing somewhere in that cloud. It's basically kind of like transporting from one location to another. So that's what's really going on. So things to remember is that, yes, these electrons can be divided into their shells that we've been talking about, like first shell, second shell, third shell, fourth shell, fifth shell, etc. But the detail that we left out was that there's these things called subshells. So within this, like for example, the second shell, there are subshells inside that shell. So just basically adding another layer. And these clouds or orbitals, the subshells, however you want to describe them, they have a really precise and particular characteristics. Obviously, one characteristic is going to be the distance they are from the nucleus, but the other one's going to be their shape. So both of those things will determine then how much energy is in that level. So here are the shapes. So we have 4 different types of shapes. We have the S shape, which is a sphere, which is that one here. We have this P shape, and you have to remember when we're talking about these shapes, we're talking about 3 dimensions, so X, Y, and Z. And so with the P shape, there's 3 different sub-shapes in there, depending on the orientation. So if we're talking vertical, horizontal, coming at you, going sideways, so that has 3 different options. There's the D sub-shape, which has 5 different options, and some of these get kind of funny looking, like that one there. And then we have the F sub orbital shapes, and that has, 7 different options. 1, 2, 3, yeah, 7. And so obviously the shapes are getting more and more complicated, and as they get more and more complicated, they're going to require more energy to exist in that shape. So that's something to first keep in mind. The other thing to keep in mind is that each one of these shapes can hold up to 2 electrons. So the S shape has 2 electrons in there. The P shape there's 3 different versions, each holds 2, so that's 6 electrons total there. The D shape has 5 different shapes, 2 electrons in each shape, that gives us 10, and then the F has 7, 2 electrons in each, that gives us 14. Are you okay with that so far? All right, I'm going to switch back to the document camera to talk about how do we then fill it in. Unfortunately, on the exam, they don't give this information to you, so you gotta have to know how to draw it yourself. So what I would first do whenever I'm trying to tackle one of these questions is I would just write down the shells. So 1, 2, 3, 4. I normally just go up to 6. So we're still thinking about our shell levels. Sorry, I don't know why it's flicking. Stop flicking. So the next thing to then think about is, why are you flicking? Stop it. Is the subshells. It's the matrix. It's trying to get through. So the first subshell just has the S. So everybody has an S subshell, which is that spherical one. Are we okay with that so far? All right. Subshell 1 only has the S shape. Once we go to 2, we then add a new shape. So 2 can have the P shape. And then everyone after that also has the P shape as well. So I'm doing P all the way down. Are we good so far? All right. The third shell, we are adding another shape. So that's going to be the 3D. And then, like I said, everybody after that also has that same subshell, D. And then the last subshell shape was our F, and that starts with 4. So 4, we get the F. Are we okay with that so far? All right. So when it then comes to filling your electron shells and subshells, let me put a little arrow to show the order you're supposed to do this in. So you start by filling the 1s. After we fill the 1s, which is really easy because it's only 2 electrons, you then fill the 2s, which is 2 electrons. After you fill the 2s, you go to the 2p. And then after you fill the 2p, you go to the 3s. So everything's makes sense quite logically. Hopefully I've done this right.
That's fine.
Okay. After you fill that, you will fill the 3p. So this is all following the same order that we've done previously. And then you go to the 4s. So this is where it starts getting tricky, because you see how we didn't finish filling the D shell? We went to the 4s instead. And the reason why is because this is a simpler shape. So even though this is further away, because the shape is simpler, the energy level is lower here than it is in the 3D shape. So that's why we're going to the 4s. And that's why the 288 rule worked up to there. So if we're looking at the numbers, 1s2, that's your 2 electrons. 2s2, 2p6, that's your 8 electrons. 3s2, 3p6, that's another 8 electrons. And then 4s2, that's your last 2 electrons. So that's where the 2882 came from. But then you have to go backwards. So this is where it starts getting confusing, and this is why we stop the story at calcium. So after I fill the 4s2, I'm going to backtrack and fill the 3D. So I fill the 3D. Once I fill the 3D, I then fill the 4p. Once I fill the 4p, then I go to the 5s. And then once I fill 5s, I go backwards and I fill the 4D. And then we go through it that way. And then I'll finish up the arrows. You shouldn't be filling anything larger than this. But that's the order of what you're doing. So you start at the end of the arrow, you finish it, then you start the next arrow. So in reality, that third shell, that orbital there can hold 10 electrons. So in reality, shell 3 can hold 18 electrons. But we go to the 4 first because it's a simpler shape. Is that okay? That was not very nice, but that's what happens. All right. So shall I give you guys an example of something off the periodic table and how to fill it in? All right, let me grab the periodic table. We can go past calcium. I'm trying to think. I might do, trying to think which one I want to do. I'll do zinc. So the F1s hold 14 because there's 7 different shapes. So if I wanted to go up, that would be 14. That's 10. That's 6. That's 2. So that one in reality, 18 plus 14 is 32, right? Yeah. And so this one, same thing, 32, 32. All right, shall we see an example? Okay. And I told you, it's a lot of work for an achieved. So, I'm sorry. They stuck this in here. All right, let's do zinc, for example. So zinc, when I look at the periodic table, it has the atomic number of 30. So what I'm going to do is I'm going to do the electron configuration for zinc going up to 30. So what you then write is 1s2, so that's my first 2 electrons. Then I go to 2s2, that's my next 2 electrons. I then fill in 2p, 6, so that's 6, 1, 2, 3, 4, 5, 6, so I'm at 10 electrons. I like to do tallies just to kind of keep track. All right, now that I've done the p, I go to the 3s, 3s2, 2 more electrons. I go then up to the 3p6, 1, 2, 3, 4, 5, 6. I fill that. I go up to 4s2, 1, 2. So I'm now at 20. All right. Then I go back to the 3d, and I'm going to use all 10 because if I use all 10, that gets me to 30. And that's the electron configuration for zinc. Lisa, are you okay? You're looking confused. Where'd I lose you?
You went from 4s to...
Yeah, so I finish the end here, and I start the next arrow. So I've gone to the 3D. And so in 3D, there's 10 that I can hold, and I need 10 more to get up to 30. So that's how this configuration works for zinc. Yeah?
Oh, and that's what you have to write?
Yep.
Do you have to explain this?
Nope.
Is that all?
Yep.
I had a calendar.
There's still a little bit more I need to tell you. It's still pretty easy though. And that's why it's only an achieved. The main thing is you need to make sure you know how to count, which is what Blake was saying.
Yeah.
All right. So are we okay with that so far?
I was gonna say this, when you're writing it,
Yeah.
you have to have the 3d10 before the port.
Yeah. So when you're writing it, in theory, you should rearrange these two. But I don't think an examiner will mark you wrong for it.
Oh, okay, never mind.
But speaking logically, these two should be swapped around.
But does it matter even?
I don't think I wouldn't mark you down for it. Yeah. I don't think an examiner would mark you down, but that is kind of the 2 accepted answers for it. There's also another way you guys can write it if you want to do shorthand, and that's by looking at the periodic table and finding the most recent noble gas. So zinc's most recent noble gas, so not going forward, going backwards, is argon. So there's a little shorthand you can do. You can write argon. Now, argon has the atomic number of 18, so basically I can skip the first 18 writing and just do the last component to it. One of the easier ways to kind of do that is, and I'll show you guys this here. So this is the periodic table with the subshells overlaid. So if I look at argon, which would be right here, it basically tells me that up to 3p6, I can just abbreviate as argon, and then anything left over I would then write as the tail. So I'll show you what I mean. So then this to this point is argon, so then I would write these last two here.
Next to Argon.
Next to argon.
In short, you just get to skip straight to 3d10.
Yeah, you just get a skip.
Oh, okay.
So if you want, that's also an accepted answer.
Oh, wow.
And you will see this as on the marking schedule. So both are accepted. So, and then when I look at this, if I know where zinc is on the periodic table, zinc is right here. So it's a full 4s shell, and then you can count the number of 3ds that you'd have to put in there. So that's another way you can do it. Charlie?
Will they give you that?
No.
No. Okay.
No. And it would help, wouldn't it? And they also don't give you this either. That's why I drew it.
They give you space to draw them in?
Yeah, because you got the spare paper at the back and stuff like that. So that's just a kind of shorthand, if that helps.
So like when you go in, that should probably be one of the first.
That's the first thing you should be writing down. It's not hard. Yeah.
Yeah.
It's irritating, isn't it? All right. Some other things I need to point out are some exceptions to the rule, and I'm happy to work you guys through it. So there's two that are exceptions to the rule. They love to ask these on the exam to make sure you know that they're exceptions to the rule. That's chromium and copper. These two guys are special simply because of their atomic number. So because of their atomic number, they can actually have either a full 3D shell or a half-filled 3D shell. And because they can do that, they're going to fill that before the 4s. So chromium, for example, has 3D5 because that's a half-filled D shell. The thing to remember when you're filling these shells is that they're going to fill each subshell first before they pair up. So since the D shape has 5 shapes, 1, 2, 3, 4, 5, and then it will start ticking over and double filling it and pairing it. Does that make sense? So what's going to happen with chromium is that instead of writing 4s 2, 3d 4, you're writing 3d 5, 4s 1 because it's stable with the half. Copper is another exception to the rule. Copper can have a full 3D shell, so it's going to go to 10, and then the leftover electron will go into the 4s. Instead of the other way around where you have 4s2, 3d 9. So just watch out for those two because those are the exceptions to the rule, and it just has to do with the fact that they can fill or half fill their 3D shell. Yeah.
I missed this slash and like it.
I'll put it on Google Classroom. I'll put the recording on there, and I'll scan the notes too. Yeah. It'll all be available. I forgot to put it on beforehand. Are we okay with that so far?
Yeah.
All right. The last thing that they're going to ask you to do for this is they're going to do electron configurations of ions as well. Ions aren't too bad. You just have to factor in if there's extra electrons or fewer electrons. So you just adjust the number that you're working with. You need to be careful, though, with any of the transition metal ions, because remember how I said, I don't know what fell down. This is why I chose zinc, actually, to show you guys it. So be careful when you guys are doing ions. So if I was doing zinc, let me grab another color. So if I was doing the zinc 2+ ion, I would then adjust the number from 30 to 28. Yeah? Now here's the wrong answer, so you guys know what it looks like, and then I'll give you the right answer. So if you filled out zinc based off of this kind of flow thingy, you would have the answer ending in 3D8 4s2, if I was following the kind of swipe table. That's actually incorrect. The right answer is you take it off of the 4s, because whenever you're forming ions, you're not taking it away from the highest energy level, you're taking it from the furthest shell. So you're actually taking those electrons off the 4s shell. Or sorry, yeah, the 4s. So you should have argon and 3d10 written down as your answer. That's the correct one. Does that make sense?
Yeah.
So just watch out for that.
What if it was only one?
If there was only one electron taken off, then you would write it as 4s1 3d10.
No, like there was only one of the two.
One of
It
the
was just 3d8.
3d8.
Yeah.
If you wrote 3d8 and you took the 2 off, you've taken now 4 electrons off.
No, like just saying like if there was a like what's it, atom or periodic table or whatever.
Yeah.
If say like you had an answer.
Yeah.
And there was no 4s2 to begin with.
Then you would take it off the 3d. Or you would take it off whatever is the furthest away. Somebody wants their cookies. So like, for example... Okay, so Caleb, answering your question. If I didn't have a 4s, the last shell I would have is the 3p. So I'd be taking off the 3p, because that's the furthest away. Does that make sense?
Yeah.
So if I was given the choice in the same shell level between the 3s and the 3p, I take it off the 3p. But if I have the choice between a 3d and a 4s, I'm taking off the 4s because that's further away. And that's all you gotta do. You get this. Yeah. All right, questions, concerns, comments? Because I know the bell's gonna go. If it actually, no, the bells aren't going. It should. I don't know if the bells are gonna go today, but the period ends at 11 because I know you guys have to get lunch.
Give us like a Electron Configuration question next week.
I'm giving it to you now.
I'm just finishing mine.
So I figured this would be a nice one to start on, and then I'll actually go into the liquids. This is just an sheet. Oh, let me
That's what you were doing, Blake. I saw you writing on this. What homework is that? I didn't get that.
You're very like concerned.
I did most of this, but then I didn't remember how to do the +2.
Positive, it's lost electrons.
So it's you just taking off that amount.
Yeah. But just be careful because if the transition middle, you take it off before.
Which one's the transition metals again? That's the ones over here, right?
That's the ones that are like in here.
Okay. Including that.
Yeah.
Shit.
So I put on the board the recommended follow-up for this tutorial. SciPack pages 10 to 25 cover this. And I'm also giving you guys a weekly exam question. So this is a nice easy one because you just gotta do the electron configurations. Like I said, it's only a cheap one. Don't ask me to check them because then I have to go through and do the work. I will literally just Google the answer. So you guys can literally just Google the answer.
Wait, so if it's a transition metal, you only take off one.
Here were the D's.
Yeah.
You take it off the S.
Okay. Yeah.
So if it ends in a 4D, take it off the 5S instead.
Okay.
But if it goes here and then you start getting a 5P, take it off the 5P because 5P is further away than 5S.
Right. You know, I'm mad that I just. Oh.
Huh?
Sorry, I'll let you speak.
Yeah.
Do we just write it exactly like
Yeah. And if you want, you can do the shorthand with argon, you can do the shorthand with the noble gases. And the good news is, if you get anything that's within the zone of like the noble gases, so if they give you a noble gas or your ion now is a noble gas, in quotations, you can just write brackets and AR and you're done. Do you want me to show you an example that's like that? So like, for example, just find something off the periodic table. All right, let's say they gave me the fluoride ion. Oh, let me just get this. So if I gave you guys, for example, fluoride, and it's F minus, its atomic number is 9, but because it's a fluoride ion, it's gained 1 electron, so it's 10. So if I look on the periodic table, 10 is now neon. So for this answer, you could just write neon in brackets and you're done. Yeah. It doesn't always allow you to do that. So like, double check what they've asked you to do. But anything that is like, if they gave you neon to write and they're like, what's the electron configuration for neon? You could just write, it's this. They probably won't let you, like, they won't do that. But I have seen every so often they give you an ion, and when you do the ion, its electron configuration is one of the noble gases, so you can just can be done.
I think this is like before I get too ahead of myself.
Yeah, let me Google the answer. All right, I'm gonna stop the recording if you guys don't have any other things. No, we're good? All right, go get some lunch.